Okay, so what we're going to do now, for the purpose of proving Cramer's rule in a little bit, is we're going to define a specific matrix that we can produce from a given square matrix. And we're going to start with something that we call a matrix of cofactors. So let's suppose for a moment that A is just any n by n matrix, and we're going to refer to Cij, as we have been, as the cofactor for the entry Aij. Then if we take the matrix that's formed by the n by n matrix that's formed by taking all of the cofactors of A and putting them in the positions that they were generated from. So the cofactor from the 1, 1 position is put in the 1, 1 position, and so on and so forth. We call that the matrix of cofactors for the matrix A. Now, by itself, that matrix not really useful for much of anything, but if we take the transpose of this new matrix, we get something that ends up actually being kind of useful, and that's what's called the adjoint of A, which we just denote this way, ADJ with an A in there. Okay, so let's do an example where we have to come up with an adjoint of some matrix. So here we have the matrix A, and what we need to do is evaluate its adjoint. The first thing we need to do is determine what the matrix of cofactors looks like for the matrix A, and that involves finding all 9 cofactors of this matrix. So I'm going to actually manually do the first 3 of them, and then I'm just going to kind of give you the rest since they're straightforward to calculate. So what is C11? Well, C11 says go to A and look for the 1, 1 entry and find the cofactor corresponding to that entry. So we delete the first row, first column. Now I'm dealing with the 2 by 2 determinant with the entries 2, 2, 1, 0. That determinant will look like 2 times 0 minus 2 times 1, which is equal to negative 2. Okay, now I need my C12 entry, which is equal to the cofactor corresponding to the entry shown here, the first row, second column entry. So I delete that first row, delete that first column, evaluate the determinant of the remaining terms, 2 times 0 minus 2 times 0. That's definitely going to equal 0. C13, what is that equal to? Well, find the 1, 3 entry, delete the first row, first column, find the determinant of the remaining 2 by 2. So that's 2 times 1 minus 2 times 0, which is 2. One thing I do want to point out here, and it's easy to not notice that with this entry that we got right here. Remember, cofactors are actually a little bit more than just finding the determinant of that 2 by 2 matrix. They are also multiplied by either a positive or a negative 1, depending on the position that we got that cofactor from. And we talked about that back in section 2.1. This first and this third cofactor that we found, both of those would be multiplied by a positive 1, which would not change what we got. I didn't mention that, but I'm mentioning it now. These would not come out any different. This second cofactor would have been multiplied by a negative 1, but because it came out to be equal to 0, that ended up not mattering. Okay, the remaining cofactors, I'm going to go ahead and just write down what they equal without talking through how to get them, since it should be very straightforward by now. C21 is equal to negative 4, C22 is equal to 0. Actually, looking at my notes here, I don't know if I wrote that down right. Let me just work that one out. That'd be, yeah, 1 times 0, negative 4 times 0. So that's 0. C23, that's equal to negative 1. C31 is equal to 8. C32 is equal to negative 10, and C33 is equal to 2. You can go through and verify these if you want to, but that's what those cofactors should work out to. So that's 9 cofactors in total. The adjoint of A is equal to the transpose of the matrix of cofactors that use these cofactors that we just found. So I'm actually going to write the matrix of cofactors first: negative 2, 0, 2, negative 4, 0, negative 1, 8, negative 10, 2, and the adjoint is the transpose of that matrix. So now, taking the transpose, remember, the first row now becomes the first column, -2, 0, 2. Second row becomes the second column, -4, 0, -1. Third row becomes the third column, 8, -10, 2. And that right there is my adjoint for that matrix, okay? That's all fine and good, but what are we actually using the adjoint for? Well, this theorem here shows what its purpose is, at least for us. It turns out that you can use the adjoint of a matrix along with its determinant to compute the inverse of that matrix. And again, this is assuming the matrix is invertible. So stated as a theorem, if A is an invertible matrix, then the inverse of A is equal to the reciprocal of the determinant of A times the adjoint of A. Remember, the determinant of A is a scalar. It's a constant, it's a real number, so this reciprocal is a scalar as well. The adjoint is not a scalar, it's another matrix. So this is a scalar times a matrix here. Notice an equivalent statement to prove would end up being this, and we'll prove this statement first, and then we'll use this to get to our result pretty quickly. So our first goal is to show that A times the adjoint of A. So if you multiply a matrix on the left times its adjoint on the right, then what you get is the determinant of that matrix times the identity matrix. Notice this would be diagonal. So we want to prove that first. Let's do that here. We're going to start by looking at that product. So again, A, if we kind of put it in a general form, might look something like this. Okay, so here's the entries, A11, A12, and so on and so forth. We end up at ANN because it's an n by n matrix. And we're multiplying that to the adjoint, which is the transpose of the matrix of cofactors for this matrix. And notice that would look like this, C11, C12, C13 below that. Instead of C11, C12, C13 going along a row, the transpose turned that row from our matrix of cofactors into a column. Okay, and here's kind of the reason why we wanted the transpose of the matrix of cofactors when we defined our adjoint. Because when we multiply these matrices, we're multiplying columns of this matrix to rows of this matrix. If I just stuck with the row with the matrix of cofactors, the thing that I wanted to multiply to a given row here would have looked like another row. And matrix multiplication doesn't do that. We want columns to be multiplied to rows. So with that in mind, let's see what happens when we perform this multiplication. Okay, so we're doing we're kind of picking the ith row from this matrix and the jth column from this matrix because that would produce the ij entry of the product of these two matrices. Now, performing that multiplication, we end up with this expression right here, ai1 times cj1 plus ai2 times cj2, and so on and so forth, right? Okay, now there's basically two things that can happen here. I and j could be equal to each other, or I and j can be not equal to each other. If I and j are equal to each other, then this can be written by replacing all of the j's with i's, since they're equal. ai1 ci1 plus ai2 ci2, and so on and so forth. But what that really is, if you think about what these represent, these c's are cofactors. And if I and j are equal to each other, then what you have is a cofactor expansion for evaluating the determinant of the matrix A. So in all of those cases, if I multiply a row and a column where the number of that row and the number of that column are equal to each other, in other words, first row times first column, ith row times ith column, or what have you, in all of those cases, we end up with the determinant of A because it's the cofactor expansion for that. Now, here's where we use that other interesting little fact that we mentioned in the previous video. If I and j are not equal to each other, then what we're doing is we're multiplying a row of A to the cofactors that would have come from a different row of A. And what we talked about in the previous video is that anytime you do that, anytime you multiply those things out that way, the result is always 0. Okay, so what does that do now when we look at this product? Well, if you look at all of the cases where I and j would be equal to each other, that would be first row, first column, second row, second column, third row, third column. In other words, where we got this determinant of A, that's going to end up in the diagonal entries of our product. And like we said, when I is not equal to j, all of those entries will become zeros, but those are all of the off-diagonal entries. And so this produces a diagonal matrix, all of whose diagonal entries are equal to A. This is the same thing as the scalar, the determinant of A, times the identity matrix. It should be pretty obvious that this is the same thing as this. So that proves what we were trying to prove in the first place. Now, since A is invertible, we know that the determinant of A is non-zero, which means it has a reciprocal. So now that I've established this equality here, I can isolate my identity matrix by dividing both sides by the determinant of A, which is the same thing as multiplying by the reciprocal of the determinant of A. So that's what's happening here. Okay, now using homogeneity, remember I have a product of two matrices here times a scalar, and we have that property of matrix multiplication and scalar multiplication that we called homogeneity, which says this is the same thing as A times this scalar times the adjoint. So I can kind of bring that scalar in between these two guys in a certain way. Okay, so that gives me this new expression. A times 1 over the determinant of A times the adjoint of A is equal to my identity. Now we use the fact that A is invertible to multiply both sides of this on the left by the inverse of A. That will cancel this A out, leaving me with the stuff in the brackets here. And on this side, I times A inverse would just be A inverse, giving me this. A inverse equals 1 over the determinant of A times the adjoint of A. That's what we were trying to prove in the first place. So now we have a formula of sorts that can produce inverses of invertible matrices. So let's do that with an example. I want to use the adjoint to find the inverse of the matrix from the last example that we did. Notice, here's that matrix, okay? So I'm going to rewrite that matrix again. The adjoint of A, which we found in the previous example, was equal to -2, -4, 8, 0, 0, -10, 2, -1, 2. Okay? We also need the determinant of A because that's showing up in our formula. Well, the matrix A was this: 1, 0, -4, 2, 2, 2, 0, 1, 0. I want the determinant of this matrix, and it makes sense to expand along the third row since we have that's the row that contains the most zeros. So I can just look at this cofactor for the 3, 2 position. I'm going to get -1. Remember, we're going to have to multiply by -1 in this case. -1 times the following determinant: 1, -4, 2, 2. Okay, that's equal to 2 minus -8, or positive 10, and then I apply the negative and I get -10. Okay, so our formula now from this previous theorem would say that the inverse of A is equal to 1 over my determinant, so -1/10, times the adjoint, which is this: -2, -4, 8, 0, 0, -10, 2, -1, 2, giving me 1/5, 2/5, -4/5, 0, 0, 1, -1/5, 1/10, -1/5. That would be the inverse of A. I encourage you, I'm not going to do this, but I encourage you to check that this worked by going back to that previous example, multiplying the two matrices together to make sure that you do, in fact, get the 3 by 3 identity matrix, because that's what an inverse should do. Okay, so now we can move on to Cramer's rule. And one thing I'm going to point out, that formula that we just came up with for computing the inverse of a matrix, we've already come up with a way of finding the inverse of a matrix, an invertible matrix. We used Gauss-Jordan elimination to do that back in chapter 1. And this technique that we just covered, using the adjoint, is not necessarily any better than that. It's not necessarily any faster. So it's not really something that we're going to say, hey, use this technique instead because it's much better. It's not really better. It's just another way to do it. And the reason we talked about it is because it's going to show up in the proof of Cramer's rule. We just need it for this proof. So let's talk about Cramer's rule. Suppose you have a system of n linear equations in n unknowns, and we're going to represent that in matrix form. A, x equals b. A would be my coefficient matrix, and because there are n linear equations in n unknowns, A is a square matrix. It's an n by n matrix. That's important. We're also going to assume that the determinant of A is not equal to 0. Remember, that tells me that A is invertible. We proved that in this section. And we also know from our equivalence theorem that if A is invertible, then this will have a unique solution. Okay? Cramer's rule states that that unique solution will look like this. If x1 through xn are the entries of this column vector x here, which would be the solutions that we're looking for in the system, then x1 is equal to the determinant of a1 over the determinant of a, x2 is the determinant of a2 over the determinant of a, and we kind of follow that pattern. Notice the numerator is the only thing changing in each one of these. Xn is equal to the determinant of an over the determinant of a, where each of those a1, a2, and a, whatever, are simply the coefficient matrix A, where the column corresponding to this index, so the jth column, is replaced by our constant vector b, the constants in that linear system. Okay, so we've already seen what this looks like in the case of a 2 by 2 system, and we're just generalizing this to the n by n case. So I want to prove this, and then we're going to do an example to wrap things up. So for the proof, let's suppose that the determinant of A is non-zero, which is in the assumption, one of the assumptions made in Cramer's rule. Then A would have to be an invertible matrix, which we have shown. And not only that, back in chapter 1, we showed that if A is invertible, this is what the solution to that system up here would look like. Our solution, x, is equal to A inverse times that column vector B. Okay? Now, here's where we want to use the result that we just came up with, because this solution, this way of finding the solution, involves the inverse of A, and we just came up with a new formula for determining that inverse. So our solution that we're looking for, x, is equal to A inverse B, but A inverse is the same thing as 1 over the determinant of A times the adjoint of A. Okay, and then we still have that B out here. So let's now look at the adjoint in a more explicit form. Remember, the adjoint is the transpose of our matrix of cofactors, which looks like this. Okay, so here's all of those cofactors appearing in there. Now, if we explicitly multiplied this matrix times this vector, I'm going to get a column vector, and it's going to look like this. So you can see from the first row, B1 times C11 appearing there, B2 times C21 appearing there, and so on and so forth. Okay, so far all we've done from here to here is multiplied the matrices. The 1 over determinant of A is still just floating around out there. Okay, now each one of these expressions in here, when multiplied by 1 over the determinant of A, is giving us one of the entries in our solution vector x. So let's single one of those out. Let's talk about the jth row. That would correspond to the solution for the unknown xj from our original linear system. Okay. After multiplying that 1 over determinant of A in, we get something that looks like this: b1 c1j plus so on and so forth. Just extracting that entry and dividing it by the determinant of A. Okay. Now what we're going to do, because remember in Cramer's rule we have these other matrices, A1, A2, and so on and so forth. We look at the matrix AJ and see how that relates to the solution that we're seeing up here. AJ, remember, takes the matrix A and replaces its jth column with the coefficient, or with the constant matrix B, the constant vector B. So looking at these indices here, A11, A1, 2, A1, J minus 1. This is the J minus 1th column. Over here I see J plus 1. So this would be the jth column. It falls in between J minus 1 and J plus 1. This would have normally been A1J, this would have been A2J, and so on and so forth, but we replaced that whole column with the B's from our linear system, okay? Now, that's the only place that this matrix differs from the original coefficient matrix A, okay? And remember, kind of like what we showed in the previous video, we did it with rows, but it applies with columns here. If I did a cofactor expansion for AJ to evaluate its determinant along this column here, then the only entries that are being used in the cofactors are entries that have an A in them. None of these B's would be used in evaluating the cofactors by themselves. We would multiply B1 times the cofactor C1J, and B2 would be multiplied to the cofactor C2J when evaluating this determinant, but the cofactors themselves would be the same cofactors that we would have gotten from just A instead of AJ. They're identical, okay? So that means that if I evaluated the determinant of AJ, I would get this expression, B1 C1J plus B2 C2J, and so on and so forth. That's exactly what we're seeing in the numerator right here. So this numerator can be written instead as the determinant of AJ. And that's Cramer's rule, because that J was chosen arbitrarily. It could have been 1, it could have been 2, or it could have been anything between 1 and n here, and that would have given us all of these solutions. So that's Cramer's rule, okay? What I want to do now is I want to find the solution to this system right here. This is a 3x3 system, 3 equations, 3 unknowns, and I want to solve it using Cramer's rule. We can obviously use a different technique. We've talked about Gauss-Jordan and all that, but we want to practice Cramer's rule. So in order to do that, I need to identify my coefficient matrix and find its determinant. So using the notation of Cramer's rule, our coefficient matrix we were calling A. What is the coefficient matrix here? 2, -1, 1. 2, -1, 1. -1, 4, 2. -1, 4, 2. 1, 3, -2. 1, 3, -2. Okay? This determinant, we're going to be calculating 4 different 3x3 determinants. I don't want to take the time to do that. We've spent enough time evaluating determinants. You can do the work. I'm just going to go straight to the answer. -35 is what we get here. Okay? What is the determinant of A1? Well, what is A1? A1 is where I take this coefficient matrix and replace the first column corresponding to that 1 in the index there, in the subscript, and replacing that with these constants, 1, 0, 5. So I'm looking at 1, 0, 5 in my first column, but nothing else changes. -1, 4, 3, 1, 2, -2. Okay? This determinant, when you work it out, comes out to -44. What about the determinant of A2? The determinant of A2 is going to take the second column of my matrix A, replace it with that 1, 0, 5, but nothing else changes. 2, -1, 1, 1, 0, 5, 1, 2, -2. This one comes out to -44. And then my last determinant of A3, that is equal to, again, come back over here, replace only the third column with the numbers 1, 0, and 5. Nothing else changes. 2, -1, 1, -1, 4, 3, and then here's where my 1, 0, 5 will show up. And I'm going to evaluate the determinant. It comes out to 28. According to Cramer's rule, the solutions to this linear system, x is going to equal the determinant of A1 over the determinant of A. In this case, that turns out to be -44 over -35, which is just, I can cancel the negatives, call it 44 over 35. Y is equal to the determinant of A2 over the determinant of A. That is equal to I think I wrote the same one down twice. Sorry, I wrote the wrong value here. This is supposed to be negative 25. I think I just copied the same thing over accidentally. Negative 25 over negative 35. Let's simplify that. We get 5/7. Okay. Finally, z is equal to the determinant of a 3 over the determinant of a. That's equal to 28 over negative 35. And we can simplify that to negative 4/7. Okay? That gives me my solutions. Before we wrap this up, I just want to point this out again. I mentioned this at the beginning of our discussion of Cramer's rule. This is not really any faster than Gauss-Jordan. It may initially seem that way. I mean, it's still a lot of work, but you may look at this and think, well, if I did Gauss-Jordan on this, I imagine I would probably do more writing. But remember that I kind of jumped straight to the answer for these 4 determinants here. And as you should know by now, evaluating a 3x3 determinant is potentially time consuming, especially when we don't have a lot of zeros to work with. You notice at most, each of these determinants only had 1 0 in them, so we can't really simplify the work a whole lot. And just to reiterate, the point of talking about Cramer's rule is not because it's a faster or better method for solving systems of equations. It's because it appears in the proofs of other techniques that you use in other areas of math. And the one example I gave was variation of parameters in differential equations. So that's going to be it for section 2.3, and that also wraps up chapter 2 for us.